For the rest of this section, we're going to be algebraically determining where a function is increasing or decreasing and where the relative extrema of the function would be. We're not going to be looking at the graphs this time, we're just going to be looking at the functions themselves and evaluating it algebraically. So the first thing that we're going to do for us to find where we're increasing or decreasing or where any relative extrema would be is we're going to find the first derivative. So we're going to find the first derivative, and then we're going to do two things with it. We're going to find any x values where the first derivative is 0, and we're going to find any x values for where the first derivative is discontinuous. Alright, we're going to find some test intervals, and we're going to test to see what's happening to the left and to the right of these particular critical numbers. And then we're going to look to see, do we have any relative extrema by seeing, do we switch from increasing to decreasing or from decreasing to increasing? Is there a switch? Alright, so we're going to follow these directions right here, and you can refer back to them in your notes. We're going to go ahead and just come on down, and we're going to look at a pretty simple function to start out with. So here we're asked to find the intervals where the function is increasing and where it is decreasing, and we're also asked to find any relative extrema. So on the test, I will give you a function that looks just like this, and I will ask you for increasing intervals and decreasing intervals. So one thing you want to keep in mind is that when we're looking for increasing and decreasing, we're talking about specific intervals, and they have to be open intervals. And then when we are talking about relative maximum and relative minimums, we're talking about actual physical points that live on the graph. Okay, so keep in mind the difference between those two. Alright, so if you're asked to find where the graph is increasing or decreasing, then we are going to first start out with the first derivative. So we're going to find the first derivative. Remember, this tells me the slope of the tangent lines at any point. So we're going to start out with our slope formula. So when I find the first derivative, of course it's going to be 6x, and this is going to be minus 4. So we're going to keep in mind that the first derivative always gives me the slope formula for the tangent line at any point along the curve. So what I want to know is, are there any places where the graph levels off? So we're looking for two things. We're looking for, first of all, is there a place where the first derivative would equal 0? In other words, do I have a horizontal tangent line is what I want to know. So let's see. Let's set the first derivative equal to 0. So it says 6x minus 4 equals 0. And then we're going to solve for x. So I'm going to add 4 to both sides. So I get 6x equals positive 4. Divide both sides by 6. And then, of course, we're going to reduce the fraction. That would be 2/3. So it says that we have a horizontal tangent line at x is equal to 2/3. So here's what we're going to do. So I'm going to label 2/3 here. X equals 2/3 actually turns out to be the cutoff point for where I could have a switch from increasing to decreasing. This is also what we would call a critical number. So this represents a potential relative max or a relative min. Alright. So this is going to separate our graph into two intervals that we're going to test. We're going to test intervals on either side. Let's choose a value to the left and a value to the right. Before we do this, what I would like to do that's important, I'm going to put my critical number in a box. Alright? The reason why is that this is the number that I'm going to use to give my intervals of increasing or decreasing. And I'm not going to use my test values. Okay, so I'm going to put the critical number in a box to say this is what number is going to actually separate my intervals. Now I'm going to pick a test value. You can pick any value that you want that lives to the left of 2/3. So any value on the number line that lives to the left of 2/3. Anytime that I can pick 0, then I'm going to pick 0. So 0 lives to the left, so let's go ahead and pick 0. We're going to pick some test values. Alright, so what lives to the right? Well, the easiest number I can think of that lives to the right of 2/3 would be 1. Okay, what we want to know is, if these are the x values that live in these intervals, what is the slope of the tangent line of those intervals? So what is the slope of the tangent line at x equals 0? So x equals 0 lives in this interval. What is the slope of the tangent line? Well, we're going to use our slope formula. So we're going to put in 0 into our first derivative. We're going to find out what is the slope of its tangent line at x equals 0. So it tells me that the slope of the tangent line is -4. Now remember what that means. That means that my tangent line is slanting downhill. So it's slanting downhill from left to right. So that tells me that the function is decreasing as I move from left to right to the left of 2/3. So we're decreasing there. Okay, what about to the right? Well, we picked a test value of 1. So let's see what the tangent line looks like. So let's put the number 1 into my slope formula. So I'm going to put the x equals 1 into my slope formula, and we're going to figure out what's going on. So it's 6 times 1 minus 4. This tells me my slope is a positive 2. So the slope of my tangent line is a positive 2. So if the slope is positive, and that's all I really care about, don't really care about the fact that it's 2, but if the slope is positive, what that tells me is that the tangent line is slanting uphill from left to right, which tells me that the function is increasing. So if I have a positive slope, then I'm guaranteed that the function is increasing. If I have a negative slope, then I'm guaranteed that the function is decreasing. All right. So we're going to go ahead and label our intervals. So where are we decreasing? We're increasing. Let's do increasing first. We're increasing from x equals 2/3. Okay, so we always use our critical number, the number there that we put in the box. We always use that as our separation of our intervals. So we're going to say from 2/3 to infinity, the function is increasing. Okay, where is it decreasing? Well, we're decreasing where we had that negative slope for that tangent line, so we're decreasing on the left. We're decreasing from negative infinity all the way to that number in the box, that 2/3. Okay, we don't have any places where that the graph is constant. Okay, the last question here is, do we have a relative max or a relative minimum? Well, do we have a switch from decreasing to increasing or increasing to decreasing? So it looks like we do. So we go down, 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 we hit bottom. So basically this is representing kind of like the very bottom. And then we start to go back up. So we're going down and then we're going up. So what does that sound like? So let's just kind of imagine it. We're going down, 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 we hit bottom, and then we start to go up, up, up. What does that sound like? To me, it sounds like we've hit bottom, which sounds like we've hit a relative minimum. So we have a relative minimum. Do we have a relative maximum? And the answer is no. We don't go up, 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 and then come back down. This would be a relative max. What we actually have then is a relative minimum. So I'm going to be very explicit about this, and I'm going to say relative maximum. I'm going to say that there are none for this graph, but there is a relative minimum, and it occurs when x is equal to 2/3. Now let's say that I wanted to know the y value of that point as well. So let's just find out what is the y value of the point on the graph that has an x value of 2/3. If I want to find these points, then what I have to do is I have to plug back into the original function, because I'm looking for points on the original graph. So I'm going to do f of 2/3. I'm going to plug 2/3 into my function that I started out with at the very beginning. Alright, so when you're looking for points, those relative maximums or relative minimums, if you're asked to find the x value and the y value, then we're going to label your x value as x equals 2/3, and then the y value will be found by plugging it back into the original function. Now you can use your calculator to do this, that's fine. I'm going to go ahead and just keep with the fractions themselves so I get the most accurate answer possible without any rounding involved. Alright, so I'm going to square first. That gives me 4/9. Squaring that fraction. I'm going to think about the 3 and the 4 as fractions. And I'm going to multiply across. Let's see here. Let's simplify a little bit before we do that. 3 and the 9 have something in common. So let's go ahead and just cancel out that common factor. And now I'm going to multiply across. So 1 times 4 is 4. 1 times 3 is 3. I'm going to multiply across here. Nothing cancels, so that would be negative 8 over 3. And then this would be plus 9. Let's go ahead and give that a common denominator. Think about that as over 1. And common denominator, of course, with the others would be 3. So that would be 27 over 3. And then I'm going to keep the common denominator and combine the numerators across the top. Okay, so 4 minus 8 would be negative 4. 27 minus 4 would be 23. So the y value that accompanies that point would be 23 over 3. So this would be also, you can also write this as a point on the graph. Alright, so this would be the point on the graph that represents that relative minimum. Okay, one thing that I recommend that you do when you're doing these is go ahead and graph them in Desmos and take a peek at what you actually did. So let's put this graph, 3x squared minus 4x plus 9, let's go ahead and put that into Desmos and just get a feel for what we just did on the graph. Alright, so I have typed in our function that we just looked at into Desmos, and I have my slope here for my tangent line. So I'm going to go ahead and move from left to right. I'm looking at my tangent line on my graph here. Notice that the tangent line is sloping down, so decreasing, decreasing, decreasing. And then the graph flattens out right there. And that's our x equals 2/3 point. A little bit hard to see because it's a fraction, but levels off right there at about x equals 2/3, which we can tell that is it's pretty close there to where we are, but a little bit hard to see it level off. We could type that in just a minute. We level off there at 2/3, and then we notice the graph starts to come back up. So at x equals 2/3, that's where we have that relative minimum. Okay, so I encourage you to try to look at the graphs in Desmos as well once you've solved them analytically, and that'll help out, kind of give you a good visual of what you just did analytically. So I put in 2/3 there, and we can see that the graph levels off there. So that has at that particular point, we have a slope of 0 for that tangent line. Okay, to the left and to the right, we're decreasing to the left and increasing to the right, so we end up with that relative minimum. All right, let's look at another example here. So we're looking for increasing and decreasing intervals, and if we have any relative max or relative minimums. Alright, so let's find, first of all, the first derivative. Remember, this is my slope formula. This tells me what's happening with the slopes of all the tangent lines. So we're first going to find the first derivative. So that's negative 15x to the fourth plus, and here we get, using our power rule, we get 60x squared. And of course, the derivative here would be 0, so we won't write that. Alright, so we're looking for two things. We're looking for, first of all, where the first derivative could equal 0. So where does the first derivative equal 0? We're going to take the first derivative, negative 15x to the fourth plus 60x squared, and we're going to set it equal to 0. Now we're going to solve for x. Now, one thing that you have to know how to do is you have to know how to factor. So we're going to solve this by factoring, and I'm going to first look for a greatest common factor when I'm solving this. The greatest common factor that I see here, I would say 15 divides evenly into both of those numbers. And the largest common factor that we have with the x's would be x squared. I'm going to go ahead and pull out a negative along with my GCF just to make, so I'm going to go ahead and pull out a negative along with my 15x squared. And I'm going to write what's left over. So here we'd have a positive x squared, and then here we'd have a negative 4. Okay, now you can always test to see that you actually factored it correctly by multiplying the greatest common factor back in and seeing that you get back the original two terms that you started with. Okay, same sign, same everything. Alright, so now I'm going to keep solving. I'm going to set each one of these factors equal to 0. Alright. So we're going to divide both sides of this little equation by negative 15. I get x squared equals 0. Take the square root of both sides, end up with x equals 0. So here's one of my critical numbers. Here I'm going to add the 4 to both sides, so I get x squared equals 4. Now really important, when I do this, I take the square root of both sides. I'm going to make sure I include the plus and minus, because we get two numbers from this when we get positive and negative 2. So we actually end up with two critical numbers, x equals positive 2 and x equals negative 2. Now you might be thinking, well, how come we didn't do that on this side with x equals 0? Well, remember, plus and minus 0 is just 0. So there's really no need to include the plus and minus with 0. We only get one number from that. So we have three critical numbers. Okay, so we find the critical numbers by looking for two things, where the first derivative equals 0 or where the first derivative would be undefined, or where the first derivative does not exist. So here would be the second question, which we didn't look at too closely with the last one, but that's okay. Where does the first derivative come out to give me something that does not exist? Well, the only time that you're going to have that is if you have a variable in your denominator, if you have some sort of fraction with a variable in the denominator. There is no place where this function is discontinuous. There is no place where x would cause a problem and cause division by 0. So this was not something that we needed to look for the last one or for this one, because it clearly would never give us a denominator of 0 because we don't have a fraction, we don't have any negative exponents, so not something that we actually need to consider. So once we find our critical numbers by setting our first derivative equal to 0 or looking for where the first derivative would be undefined, we're going to take those critical numbers and we're going to put them on our number line. So I get negative 2, and remember we're going to put them in boxes. I get 0 and I get a positive 2. So I'm going to put the critical numbers in boxes. Now what we want to test to see is what's happening to the left and in between and to the right of all of these critical numbers. We're going to figure out what the tangent line looks like. What is the slope? Is it positive? Is it negative? What's going on? So we're going to choose some test values. So I'm going to choose something to the left of negative 2, which is going to be negative 3. I'm going to choose something in between negative 2 and 0. I'm going to choose negative 1. Choose something in between 0 and 2. I'm going to choose positive 1, and then choose something to the right of 2. I'm going to choose 3. So you need to choose test values to the left, to the right, and in between all of those critical numbers that we found. Alright, I'm just going to draw some lines kind of separation. So we want to know what is the slope at x equals negative 3. In order to do that, we're going to plug negative 3 into our slope formula. Remember that the slope of the tangent line, that formula comes from the first derivative. That's what the first derivative is. So we're going to plug negative 3 into the first derivative. So negative 3 squared to the fourth, times negative 15 plus 60 times negative 3 squared. And you can throw all that into your calculator, whatever you want to do. We want to figure out if this is going to be a positive number or a negative number. So let's throw that into our calculator and see what we get. So I end up getting a negative 675. Just throw that in your calculator there, which tells me that on to the left of negative 2, since the slope is negative, and that's really what we care about, not the number specifically, but the fact that it's negative tells me that my slope, my tangent lines are going downhill, my slope is negative, tells me I'm decreasing as I move from left to right on that particular interval. So we're just going to do the same thing for all of our test values. We're going to throw them in. So the first derivative, we're going to throw in negative 1, and we're going to throw it just right in, just like we did with the negative 3. And then we're going to see what number we get out. This one's actually pretty easy, don't really need much of a calculator for. Negative 1 to the fourth, we know that's going to be a positive 1. Positive 1 times negative 15, negative 15. Negative 1 squared is a positive 1. Positive 1 times 60 is 60. We end up getting a positive 45 there. So that's a positive slope for the tangent line. It tells you my tangent lines in between here are slanting upward, which tells me that the function is increasing on that interval. We're going to do the same thing with positive 1. We're going to throw that in. Let's see what we get out from that. So this one's actually pretty easy as well. We get negative 15 and then obviously plus 60, which gives us another positive 45, which what I care about is the fact that it's a positive slope, not the slope is specifically 45, but that it's positive. So we have another increasing interval between 0 and 2. And then lastly, we're going to test out to see what is the slope for positive 3. And we're going to throw that in just like we threw in all the others. And of course, once again, you can put this into your calculator and see what comes out. You'll notice it should be the same as the first one there. I end up again with another negative 675. So the slope is negative. Don't care necessarily what the number is of the slope, but the slope itself turns out to be a negative number. So it tells me that I am decreasing. All my tangent lines are slanting downhill, which tells me we're decreasing on that particular interval. Alright, so where are we increasing? We're increasing from negative 2. We can just go ahead and say, since we're increasing from negative 2 all the way to 2, that we're just increasing over both of those intervals. So 0 is included in the domain, so we're just going to say that we are increasing from negative 2 all the way to positive 2. Alright, so we're increasing all the way. Where are we decreasing? Well, those are not touching, so we'll say that we're decreasing from negative infinity all the way to our cutoff value of negative 2. I'm just going to put the word and there. You can use something else if you want. And then we're also decreasing from 2 to positive infinity, so from 2 all the way to the right of our graph. Alright, so there's our increasing and decreasing point intervals. Where do we have a relative max or a relative minimum? So let's see. It looks like here we're going downhill, then we go back up. So this right here would represent a relative minimum. So we're going down and then we come back up. So at x equals negative 2, we'd have that relative minimum. What about 0? Now when we look at 0, we're increasing to the left, so we're going up, 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 and then we hit 0, and then it still says go up, up, up. So this is not a relative max or a relative minimum. Okay, so this is neither one of those, so we're not going to report that one. Alright, so what happens between the other box number to the left and to the right? So we're increasing, so we're going up, 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 and then we get hit 2, and then we start to come down, down, down. So it looks like at x equals 2, we have a relative max. Okay, so we have a relative maximum at x equals 2, and I'm going to go ahead and just report these as points. So I'm going to say at x equals 2, looks like we have a relative max. At x equals negative 2, it looks like we have a relative minimum. I'm going to go ahead and give the y values of these points as well. So if I want to find the y values of these points, then how do I find those? And let's just remind ourselves, these are actual points on the original graph, so we need to go back to the original function. Not the derivative, but the original function. So if I want to find points on the original function, then I'm going to need to plug back into the original function. Okay, so we're going to plug in 2, and I'm going to plug in negative 2 into the original function, and we want to see what y values that we get out. Okay, so let's plug in a positive 2 first. Okay, and you can just throw all of that right into your calculator. Should be a pretty easy plug in there. I'm going to get out a 40. So I'm going to leave the calculation to you there for those. Really pretty straightforward. Let's go ahead and write a 2 there for that. I'm going to go ahead and write out my original function, and then we're going to put in a negative 2 this time. Once again, really straightforward calculation in your calculator. Just throw all that in at once, and you end up with negative 88 for that one. So we have the x values of the relative maxes and relative minimum points, and then we also have the y values that go with them. Okay, once again, I encourage you, take this function, I'm not going to do it for you this time, but take this original function, plug it into Desmos, and see that all of this that we have come up with here, all of this is really true. Plug it into that tangent calculator and just see that it does ring true everything that we have said about increasing and decreasing intervals and relative maxes and relative minimums. I think it's important for you to play around with Desmos to get that visual picture of what we have analytically discovered here.